on 9-7 in class. Now would be a great opportunity for you to ask questions on anything that might have been confusing to you, anything that you might have been unsure about. Why would it be a great idea to ask questions? The answer is what? Why would this be a good day to ask questions on this stuff? Yes. This is like what the exam is going to look like, 20% of your exam. We'll be doing we'll be doing a limiting reaction problem to what you see here. So if you're having trouble on any part of this, now's the time to ask. How do we do on balancing the equation? How about this page right here? Is there anything that you're having trouble with? Like, I'm not sure what you're doing here. I'm having trouble with this part. All right. So with the 34 grams of ammonia, how much of the nitrogen monoxide can we make, the NO? Correct. 60 grams. We have enough ammonia to make 60 grams of the product. We have enough oxygen to make 96 grams. So what's the limiting reactant? If we have enough oxygen to make 96, then we only have enough ammonia to make 64. What would be our limiting reactant? Here's our reactants. Let's see if I can raise this up just a little bit. The ammonia can make 60 grams of the product. The oxygen can make 96. So what's going to be the reactant that limits how much of the nitrogen monoxide we can make? Yes, the ammonia. We only have enough ammonia to make 60. We have a lot of oxygen. We have enough to make 96. The one that makes the lesser amount is the one that's going to limit it. Very good. So as we see here, ammonia would be our limiting reactant. And we would only be able to make 60. So the next question they're asking is, how much oxygen did we really need then? We used 128. Is that what it said up here? We used 128 grams. But we probably put more oxygen in than they needed. Why would they have put more oxygen in than they needed? What's the point of having more oxygen there than we needed? What's the point of that? Why would they do that in a reaction? Put in more than they needed. Oxygen is the excess reactant here. And by putting in more, we can assure that all the ammonia can find somebody to react with, can find the oxygen to react with. So the lesser reactant, the one that's less expensive, the one that's essentially free, the oxygen, you want plenty of it so that all the ammonia molecules can find oxygen. So how much did we really need? How much did we really need? How much of the oxygen do we need to react with the 34 grams? It turns out we only needed 80 grams. So when the reaction's over, if we started with 120 grams, we used 120, we only needed 80, that meant 47 grams of it, 47.93 grams of it, of the oxygen would still be floating around unused. Does that make sense what they did there? Questions on any of that? Then the last question. Most reactions you're not going to make. Yes?
I was kind of confused on the answer for before. How would you deal with that? I'm just confused on that.
Theoretical means how much could we make if everything went perfect? If every ammonia molecule found an oxygen molecule. If none of the reactants or none of the products was lost, none of the reactants were spilled. Number 4, theoretical yield is how much could we make if everything went perfect. We have enough oxygen to make 96 grams. However, we only have enough ammonia. 34 grams of ammonia can only make 60 grams. So that's the most we could make, 60. That gets us back to what do they mean there? Well, if I have 1, 2, 3 pizza crusts, but each pizza crust needs a can of pizza sauce, and I only have 2 cans of pizza sauce, how many pizzas could I make? 2. Well, I have enough oxygen to make, 96 grams? That would be like having 3 crusts. But I only have enough ammonia to make 60 grams. So that's the most I could make. There was extra oxygen in the reaction. So where did they get how much could we theoretically produce? Only 60. We couldn't produce 96. Why? I don't have enough ammonia to produce 96. Ammonia is NH3. I only have enough ammonia to make. So that's what they mean by limiting reactant. Limiting reactant is the one that makes the smallest amount of product, and that's what you're going to make, the smallest amount of product. Did that answer your question?
Yeah.
Right here, though, if everything went perfect, we could make 60.04 grams, but they told you we didn't. We only made 58. So somewhere 2 grams might have been lost. Maybe not all the ammonia's found oxygens. Maybe some of the nitrogen monoxide escaped before we could collect it. What's our percent yield? Percent yield is what you actually made divided by what you should have made times 100. That meant 97%. We were able to get 97% of the product. These problems are muy importante. This is a major type of calculation you should know how to do. For that reason, we're going to practice it again today. We will practice these again today. But taking a look at today's work, I'm very fond of this assignment. We're going to do 9-8 today, which has one of the most famous, this is based on one of the most famous chemistry demonstrations. Are we looking up here? This is called the what demonstration? It's the barking dog demonstration, which is a fantastic demonstration. So you'll get to watch the demonstration. It involves something called nitrous. Some of you probably heard of nitrous before. If you haven't, you'll hear a lot about it today. As you read through this, nitrous oxide, sometimes called, or more properly called dinitrogen monoxide, is used in motor racing. You'll find out why they use that. Have you ever heard of having an engine running on nitrous? That's where nitrous is shot into the cylinder with the gasoline that's burning. And there's a reason they do that. Because when your gasoline explodes, all you're trying to do is cause the piston to move. But by putting nitrous in there, you generate more gas. Because when dinitrogen monoxide, nitrous breaks down. If we have 2 moles of N2O2, we actually make 2 and 1, 3 moles of gas. So the moles of gas goes up. So that means that this reaction will help create more gas to cause that cylinder to move. Likewise, one of the products of the decomposition of nitrous is oxygen. What do we need to combust the fuel? Oxygen. So the product of the decomposition of the dinitrogen monoxide, the nitrous, actually is producing oxygen to help the gas fuel burn. As you'll see, a lot of people think that the nitrous itself is burning. Well, actually, it's decomposing. As we see here, nitrous itself tends to be a non-flammable gas. But the heat of the engine or whatever causes that molecule to fall apart, decompose. But you'll get to see Jimmy Kimmel is actually in on that. Have you heard of Jimmy Kimmel? Yeah, he's actually there watching the barking dog demo. He thinks it's pretty cool himself. And then there's another really cool version of it right here. So there's two versions of the demo. In this particular thing, what they're doing is reacting. The barking dog reacts nitrous with carbon disulfide in this reaction right here. And you'll have to write and balance this reaction. You balance that one before you do it. Be sure you balance it before you do it. This is not balanced. If you have trouble balancing, this is not a hard one to balance. But if you have trouble, click on the link and it'll show you how to balance it. And then we're going into the problems. Mass to mass, limiting reactant problems. And then we end with a new problem to take us to our next discussion. Look at our final problem here. They're adding a new one. Are you watching? Some of you are not looking. Please be watching here. Our final problem, they're asking what volume of N2 gas would be produced from this mass and this mass. They're now asking for a volume in liters instead of a mass. So this is no longer a mass to mass. You see that? This is no longer a mass to mass. Now on this problem, what I need you to do is cross out here. We're only going to do one of these. So cross out that. We're going to find out what volume of N2 gas we can get from 176.08 grams of N2O. You see what we're doing? There's no setup. They didn't provide you with the setup for that second problem, so we're not going to mess with it. We're just going to do this first one. Is everybody good? Did you understand what I just said? Cross out that second part of the problem. You only have to do one of these. Now, how do we do this? Now we're no longer going mass to mass. We're now going a mass to a volume. So where are we on the chart then? When we take a look at this chart, where are we? If you look at the assignment here, you see the chart? We've been going mass to mass. We're no longer going mass to mass. This is the first time we're going mass to something else. We're given a mass. Now where are we going? We're going up here to a volume. So our setups would be this one first, this one second, and this one should be third. You see that? This is like our first chance to explore other places to go other than mass to mass. Good luck with the assignment. You may work together on this. The answer key is posted. Do not copy off the answer key. Use it to check and correct your answers.